So Professor Rohit Buddhiraja is a faculty member in Department of Electrical Engineering, and more important, he is the Vice Chairman of Bharat 6G Alliance. So that's a more responsibility. Specializing in wireless communication, signal processing, next generation networks, he holds a PhD degree from IIT Madras. His research focuses on multi-antenna systems, cooperative communications, energy efficient 5G and 6G technology. With this, let him welcome him, and I welcome the other panelists as well. So, Professor Mathini, are you here? I think she's, yeah. Welcome. She represents the uh, Heriot Watt University, Scotland. Welcome, ma'am. I think you are here. And I'm sure that, let me read this Professor Mathni. She is IEEE Fellow, is a Professor of Signal Processing and Wireless Communication and Dean of Science and Engineering at Heriot Watt University, UK, with over 20 years of research. She has published 200 plus papers and 2 monograms focusing on wireless communications, machine learning, radar, and assistive technology. She has held research positions at Bell Labs and Canadian Communications Research Centers and received multiple awards, including the IEEE WIE Mentorship Award. She serves on several advisory committees and is a fellow of AAIA, FAIIM, and the UK Women's Engineering Society. Welcome you, ma'am. Next, we have Dr. P. Hanumanta Rao. Mr. Rao, oh, welcome, sir. Welcome, and sir is a DG of Samir. I think that's his, one can say, more than sufficient introduction. Sir is heading that and is spearheading, I will say, RF part of the country, and sir has been given the responsibility of one of the 6G test lab very early, and you can read other things from this one. Next, I welcome Professor Nandana Rajatheva, University of Olu. Sir, please come. Professor. So, sir basically represents us our 6G flagship Olu University here, and we are grateful that sir you came and represented. Sir holds a BSc from University of Muratua, Sri Lanka, and MSc and PhD from University of Manitoba, Canada, with the over 200 publications. Research focused on 6G physical layers, machine learning, research allocation, multimodal sensing, and channel coding. Next speaker we have Professor Eric Strom, Chalmers University, Sweden. Welcome, sir. And Professor Eric, again IEEE Fellow, Head of Division of Communications, Antennas and Optical Networks. His research focus on signal processing, coding modulation, channel estimation, wireless positioning, vehicular communications, and low latency, ultra reliable communications. He has received multiple awards, including the Chalmers Pedagogic Prize, Supervisor of Year, and the areas of Advanced Prize. Welcome you, sir. We have Professor Debrati Sen from IIT Kanpur. Welcome you, ma'am. I know that you traveled. Sorry, Kharagpur, IIT Kharagpur. And ma'am's interest, National Doctor Fellow of India, and holds a PhD in Telecommunication Engineering from IIT Kharagpur, and is a postdoctoral research fellow at Chalmers University, Sweden. Formerly chief engineer at Samsung Electronics. Her research focused on wireless and optical communications in coherent optical systems. So I think being in the industry, ma'am is more relevant how to convert industry and academia collaborations. Welcome you, ma'am. We have Deepa Venkatesh, IIT Madras. Welcome, ma'am. I think she is also heading one of the 6G research test labs at IIT Madras. So there were the 2 6G test projects sanctioned initially. So she is currently professor with the Department of Electrical Engineering, IIT Madras, and she has authored more than 100 publications in international peer-reviewed journals and conferences. Her research interest includes optical communication system, but more important, she is steering the advanced optical test bed project at IIT Madras. Professor Cove Delpenjori, University of Glasgow, UK. Welcome you, sir. In case I am unable to pronounce properly, so kindly pardon me. So, Professor is Royal Society Industry Fellow in Quantum Computing and Associate Professor at the University of Glasgow, UK, where he leads the Quantum Information Cluster. His research focuses on quantum information processing hardware, and he has received numerous fellowship and awards, including from the Royal Society and Royal Academy of Engineering. He is a fellow of the Institute of Physics, senior IEEE member, fellow of UK Higher Education Academy, and editor for IEEE Transaction and Quantum Engineering. So I think I have all the eminent panelists. Now I hand over this back to Professor Rohit Buddhiraja, the moderator of session, for steering for 1 hour. Over to you, sir.
Thank you, Rajesh. So since I am the moderator of this session, I requested each one of the panelists to make a small presentation, and once they finish their presentation, we'll have Q&A, and then we'll open the floor for the audience. So I request each, so we'll start from maybe from Deepa, or we can start from you, Deepa, you can make a presentation.
I think Rohit is asking me to start because light travels the fastest. And if you're doing optical communication, right, the latency is low and capacity is high. And we need to speed up there. All right, so this is something which is dear to my heart, how photonics becomes extremely important for 6G, right? For several years, optical communication and the wireless communication were probably running separately in silos. One group was not talking to the other, or rather, all the front haul, back haul, all the connectivity was assumed to happen in optical communication. Then came coherent communication, where we were increasing the data rates, and we started using the same or similar approaches of signal processing in the optical communication domain, right? I learned digital signal processing from David, who's probably, you know David, right? And we started doing coherent communication with the signal processing for that, taking cues from wireless communication. Now I think it has come to a point where both are inseparable, right? We cannot really, it has to happen seamlessly, especially with what we are talking about in 6G. It has to happen a seamless connectivity. So I'm just going to take the next 1 minute. Can we change the slide, please? Oh yeah, thank you. Oops. To talk about what is critical, what I think is critical, and what needs to get included or paid attention to. One is the optical fiber infrastructure, which would ensure or continue to ensure ultra high capacity, low latency, front haul, back haul data center interconnects, right? So some solutions which are emerging are high speed transceivers. So the high speed transceivers can go up to the speed only up to the point where the electronics can grow. So use something different like space division multiplexing, where you're using multi-core fibers or few mode fibers or something. Hollow core fibers for low latency. The second point is advanced optical signal processing itself, where the handovers are happening with very high reliable connectivity, with high energy efficiency. We should seriously think about analog plus digital processing so that the speeds can be achieved better. Electronic photonic integrated circuit integration. You can't treat photonic chips separately from electronic chips. They have to be co-integrated. The third point is all photonic networks or all optical networks, where the conversions from optical to electrical or electrical to optical does not happen in the switches and routers. It has to be a seamless optical path, right? and we need to do with all optical switching routing solutions. The fourth point I have is free space optics and Li-Fi, where front haul, back haul connectivity, where fiber is not accessible, all these lights could be giving us the Li-Fi signals instead of Wi-Fi signals, right? And the last and probably the most important is security. And I strongly believe continuous variable solutions with traditional coherent transceivers would be the way to seamlessly grow into giving security through QKD. In addition to the single photon source, single photon detectors, maybe those are for specific applications, but if you want to seamlessly grow with coherent communication, this seems to be a good solution. These are some points, and this discussion is about collaboration, and all this technology is expensive, right? It's all very, very expensive. They are highly complex, interdependent, multidisciplinary. The relevant challenges, the globally relevant challenges, they demand collective expertise, shared resource, access to foundries, packaging. All this will make our transition much faster. And of course, the most important, we all work together to get to harmonized standards so that something that gets developed in India doesn't have to go through another standardization process if it gets used in some other country. With this, I will stop, and thank you.
Thank you, Deepa. I request Dr. Rao to make his presentation.
Doesn't display there? Right. I'll be taking through the kind of challenges we face while building the 6G technologies. We talk so much about the data rates and creating the massive MIMO systems, and as Professor Deepa mentioned about the optical communication, all the places we have the issues with the hardware. And we assume that things are available, we build the models and we build the algorithms, and finally when you try to implement it, then we start finding the difficulty of what we promised, what we thought it possible, and reaching a very simple as simple as FPGA is not available for us to get the data what we wanted. So these kind of the complexities just want to take you through. I mean, most of things are relevant for everybody. I mean, spectrum and interference, most of the time we try to work about the existing models and expect our entire deployment to work on somebody else's model. So that's one thing which is probably we need to change our mindset of when you deploy our own solutions for our environment, we need to have our own model as per the spectrum. It could be terahertz sensing or even a 7 gigahertz model. I mean, the way people talk so much about AI, at least we can extrapolate the existing model for the environment where we are going to deploy our solution. That's one of the very critical thing which you have been missing most of the time, which works on paper when you deploy in a particular part of the entire deployment scenario. Some places your cells are working, some places cells are not working, and we apply the same model all the places. So we found that as one of the critical disadvantage when we build the entire 5G solution deployed at multiple places. Then probably the antenna designs, that's one thing which is close to our work and research. IRS, intelligent reflecting surfaces. You go around and see everybody is building an IRS. You find multiple demonstrations, and everybody says that is going to change the entire 6G deployment. And I can assure you it's going to be a challenge. Whatever I've seen, there is a small piece of board with a few hundreds of the elements there, and seeing that I'm steering the beam, and they added intelligence. I have the wonderful algorithm, steer the beam, and I have the dynamic beam steering. All becomes too complex. It comes to the deployment. Each vector you use it, each pin diode what you use, and the way you start putting them into the wall size IRS, it is prohibitively expensive. Unless we need to come out of some kind of a meta surface or some kind of a material which can steer the beam by just biasing it or finding some mechanism, and otherwise this deployment of IRS on a commercial scale, it's going to be very, very challenging. It isn't easy. We also have a lovely demonstration using vectors. We can create the single beam, multiple beams, steer the beams independently. All that is nice for the lab. You're expecting that I'm creating a non-line of sight communication using IRS, converting one of the panel in the building into a IRS surface. You're paying large amount of the money, which is not practical. So that portion of it is not been looked at. How to create the device, the conceptually the way you use the periodic structure and using the devices, biasing them and supplying the voltage, changing the impedance, it's not going to work in large scale. Not that the functionally it works. So you need to come out with different kind of approach as a surface, then probably you'll be able to steer the beam. Then of course modulation, people are smart enough to build full duplex OM and all the stuff there. The place where we always get into the roadblock, the devices, high power devices. Now we are moving to 7 gigahertz, expected to be one of the deployable, the frequency bands. Even at 3.5 gigahertz, when we start working front-end modules, you have 6040, 64 MIMO system, and the number of the amplifiers we use and that kind of transceiver systems, it was prohibitively large. We could manage it. It's 3.5 gigahertz still is doable frequency. And 7 gigahertz is the new band. It's neither falling on the next band, not falling on the extended C band. At this 3.5 falling in the C band, we have access to the devices. At this 4.2, 4.4, still we have the altimeters, radars available there. The 7 is not really. 8, you get the lot of devices. So unless you have a large amount of the research in the affordable production at 7 gigahertz devices, especially front-end modules and the power amplifiers. And 7 gigahertz, you know the path loss which is expected to come, and you need large amount of the power amplifiers and the thermal. That is going to the one which is going to kill the entire system. You expect 6040, 64R at 7.5 gigahertz. The amount of the power you want to dissipate on the RRH is going to be too large. So you need to come out with a very innovative way of, that's what we address to the enabling devices, both materials and how to take over the heat when you have such a large system and multiple amplifiers in the system. Remaining, I'll skip it. And if you look at the devices, I just marked a few of them in the bottom. The last one, we are more interested on the periodic table 3 and 4, semiconductors, where we use the gallium nitride and where we need to have the amplifiers. That's one of the critical components going to be the front-end module of the 6G deployment. And in terms of the speeds, you see that you want to have large speeds, invariably have to end up in the photonics transceiver systems. As Professor Deepa mentioned, we don't have a choice. You won't have over a very, very large distance, none of these systems can work. If it's a free space optics or the through optical fiber, we need to have a kind of a hybrid approach. We need to have some kind of a convergence of these two technologies. Otherwise, we don't get as the frequencies move up, expecting to get the same amount of the range is going to be very, very difficult. Then getting on to the antennas, the MIMO systems, what used at 5G, whether it's typically can be replicated at 6G, we are not sure about it. As I said, in terms of the cost and the technology limitations of having the 7 gigahertz systems there, whether will it come down the cost, which is deployable solutions, or people try to do some other roundabout way of doing it. We're not pretty sure about it. If you look at, if at all, from maybe just another 30 seconds. So probably you want to bridge this gap. You need to think more holistic way than that who is doing what we are doing it. So look at from that perspective, we need to have a significant R&D which can come from multiple sources. We need to do that in such a way that start taking the basic component what we need for the entire chain. Start from the antenna to down to the baseband. I mean, everything cannot be built by everybody. So somebody can take the front-end module, somebody build the amplifier, somebody start with the mixers, somebody start doing the LNAs, somebody start looking at the multipliers. You need to create that kind of an ecosystem, do the entire approach, a kind of a large approach of the building the devices or the components for the 6G, at least 7 gigahertz band, and combine them as small subsystems, integrate them, create the smaller system, then finally move towards to a single IC which can do the job, keeping amplifier out. So unless you follow that kind of approach, at least down the lane in 3 years, we will not have a solution which is adoptable for our own environment. So I'll stop at that point. Probably we'll take up during the discussion. Thank you.
Thank you, Doctor. Can I request Professor Madhini to present now? Thank you.
So good afternoon, everyone. So, my research area is mainly signal processing, and so I see from the point of view of the foundational and emerging technology enablers for 6G from signal processing point of view, and pathways for global collaborations. Okay, so in a nutshell, we know that we have a long history coming to this point of 6G. So up to 5G, so we went from analog to digital, and mainly it focused on mobile communications. How we actually going to provide enhanced mobile communications over the years, and some may argue that the IoTs and user directed data services has happened from 4G, but the main device was mobile phones. But from 5G onwards, the expectation changed. Yeah, we were looking into more user cases, edge cloud processing rather than doing everything on the phones or devices that we have. And it became much more complex, and also it became a global presence. And then the reduced capability devices are introduced now, and it is expected to have more user cases with compelling business case as well. So to make the 6G success, we need to have a business case for the application that we are going to take on. Under this, I thought there's two visions. One, the first came from Simon Heikin in the cognitive dynamic system. He visualized this as a intelligent network system. And also recently, that was an academic view that came like almost 20 years ago. And recently, from Harold House and Malik Tatipa-Muller, they also visualized the network as a biologically inspired cognitive model. So this is a direction we are going, but whether we're going to achieve in 6G, or it's going to be 6G advanced, or even beyond, or it doesn't, it may not happen in 5 years, but maybe this is a direction that we're going to go for the next 20 or 30 years, to bring the network as much more intelligent. So in this direction, the question I have is the sustainability. You know, the energy, the amount of energy that we are taking is going to increase because the demand for the communication and also for users applications are going to grow exponentially. So we're expecting to see like billions or trillions of devices. So the energy is going to grow. So I think for 6G, I think if you're going to develop anything revolutionary, I think one thing that we have to keep in mind is the sustainability, the energy usage. So in order to do that, there are, I mean, it's just been a consideration for many, particularly in the academia, and also I'm sure the industry who are the one going to develop and make the business cases. So for them to sustain, they're also very keen to reduce energy. So there are a number of technologies that already that you're aware that I have listed here. One is the AI native network architecture. So AI native means it's going to be integral part of, you know, control plane, user plane, and service orchestration. Everywhere the AI is going to be. But the AI is itself energy consuming. It is a chicken and egg problem. Like, you know, you can reduce energy by using AI, but current AI takes so much of energy. It's energy hungry. So we need to define what is AI is going to be in the communication system or communication network or 6G domain. It doesn't have to be the conventional one. How are we going to use the native technologies within the communication network is going to be a challenge. Another one is integrated sensing and communications. Again, it's again an additional role. So it is going to be challenging in the sense, how much reliability it's going to bring for us, and whether it's going to consume further energy and so on. So there is a number of things for academics to actually involve with industry to understand these domains. And again, the higher frequency, as mentioned, like it is going to be energy consuming. There are no devices that are usable in different frequencies, so that's another domain to work on. The reconfigurable energy intelligence surfaces, it's one other place that can be used in particular cases, but it can increase interference if you start heavily using it. So that's another domain, how far that we can go into that direction. And definitely non-terrestrial network, as you said, many use cases will require satellite. Satellite's been there for many years now, and it is integral. It's kind of a skeleton for us to carry on the telecommunication in the 6G as well. So one other thing is the optical communication is raised. Like, optical is one that connects us mainly. The wireless it's a cream, but the optical network has become the major part of it. And it is very clear that the optical network can't sustain if you don't have foundational technology improving, and particularly quantum technology has to improve for optical communications to sustain. So we have a lot to work on 6G, I believe. So just for academia industry collaboration, I thought that we have a really nice framework, and Professor Harold Haas is here. He's one of the 4 key people who actually founded this. It is called Federated Telecom Hubs in UK. There are 3 telecom hubs looking from communication system perspective, material science, everything on that part, network of networks in the network side of it, and distributed communication is another side of it. In addition to that, there is another team of people working to bring test beds aspect of it, along with the multiple universities. So that's very, very important. So we have Titan, which is networks of network communication system, and then distributed system, and integrated test bed. And then I'm part of Titan, the networks of network, which is led by Harold Haas here. And it has many different aspects, like network convergence, RF wireless communication, optical communication, optical fiber networks, non-terrestrial network, and quantum network. So it's being part of a large group. And we do some work at we're looking into millimeter wave for certain applications. So it's a user case for particularly robotics and assistive care robotics, how the millimeter wave can, actually reliable service to provide network connection for robots or something like that. But being part of this major network brings us a connection between academia and also industry. Like, rather than every university have their own system working for individual academic, this is like 25 different partners together, and we have a system that they develop which actually support us to look into or talk to industry, and also whether we need to protect the IPs or whether we can publish, and various other aspects are monitored under this framework. It's maybe an example for other people to follow, and another challenge is how we can actually bring it as a global network. In order to do global network, the main problem is IP, the preservation of IP. To bring joint testbed, we need to have proper policy harmonization and framework developed. And there are many other challenges that we had to look into it. So yeah, I'm looking forward to something like that happening in the near future. Thank you.
Thank you, Professor Madhini. And now I'll request Professor Nandana to make a presentation.
Right. Good afternoon, everybody. So I'm going to talk a little bit about what are the trends and activities in this 6G development. So yeah, I represent this 60 flagship project, which has been running now for 8 years. So I'll quickly go through a couple of slides. So yeah, as already Professor Madini showed, so we have been evolving from lower generations to higher generations. So one question actually that I have at the end is that what will happen this, let's say 6G or beyond 6G, whether we have a resilient, sustainable and AI-driven society that one will be looking into. So on that, I think this is my main slide. So can we have this resilient by design? Because there are a lot of issues that that are happening across the world, different kinds of distortions in the system or the failures of the system. So can we predict those systems, and can we get preemptive action on that? So this is one thing that we are keenly looking at, how we can make the wireless systems resilient, right? So the other thing that we have this test network at University of Hull, which is connected to other universities as well. How do we make this resilient and incorporate this resilient aspect? And we are also incorporating this Aquata system by NVIDIA, and we are working with this AI RAN Alliance together with Nokia and other companies. And yeah, so some of these activities that are along those lines, like AI-driven communications, very briefly, different aspects of physical layer. And we are working essentially in my research, AI 4N, of course there is AI other aspects as well. And this is of course another key thing that we have been discussing, how to combine communication and sensing, especially multimodal sensing. We have a lot of cameras, LiDARs, so how do we combine them with radar together with providing digital twins and come up with an integrated solution that we are demonstrating. We have a couple of demos in Brooklyn, New York Summit as well. So this is joint work with NVIDIA. And like I mentioned earlier, so in terms of collaboration, we have started the white paper on resilience. Anybody can join this one. You can just search on that. And we have finally, so these are the main sections. Of course, these can be modified as we go on. Different aspects of resilience. And yeah, finally we have this resilience summit. So you can look into that and see how you can collaborate on this white paper and part of this global activity. Yeah, thank you.
Thank you, Professor Nandana. Can I request Professor Devrati Sen to make her presentation now?
Good afternoon, everybody. So to add on, I will be also highlighting some of the enabling technologies for the upcoming 6G. I see actually the designs and the development that are expected to happen mainly in the 4 pillars. The first one is the AI native core, where the intelligence embedded into the network fabric. But it is just not to be an add-on case. It will be integrated with the sensing also. So integrated sensing and the communication that we are planning to see today, that it will be only sensing, it's not like that. For example, if you add the integrated sensing with the upcoming UAV networks and the US, it will be also controlling the movement. So the sensing, movement, communication, further prediction, integrating with the existing 5G networks. And if I expand the integrated sensing and communication to the multi-rad communication, where actually the air, ground,
communication will be integrated, space, air, and ground communication. There also actually the integration of the sensing and movement and communication continuously needs to be coming into picture. The third pillar is coming with your sustainability design. We have to actually think that energy efficiency will not be the last goal. Energy efficiency should be our primary goal for going ahead. So green communication should be the first point to think about, because we are talking about in enhancing our transmission frequency, widening our transmission bandwidth. So both will be asking for us to go ahead with the integrated massive gigantic MIMO communications, which are all power hungry. We are talking about the quantum computing. We are talking about integrated sensing and communications, and also the multimodal sensing. All these activities are really energy hungry applications. So energy efficient solution from the beginning itself should be enabled in our designs. The last one is the global coverage, which is talking about the ubiquitous connectivity. Here also actually we are talking about the non-terrestrial network to becoming an integrated parts of the commercial communication and cellular communication networks. So all the LEO satellites that they will be communicating with each other, or all the interplanetary missions that we will be targeting for ourselves, connecting the satellite data, transmitting them through the HAPS to the UAV networks, to the ground satellite base stations, to the ground base stations, satellite to base stations, the seamless connectivity that we are thinking about, that has to be connected with this ubiquitous communication and the global coverage. The seamless connectivity from the space to the ground to the underwater, that's what we are targeting for. See, for going ahead with the waveform designs will be our another key enabler part to go ahead with all these 4 pillars. See, mobility is coming up, another integrated part for us. We actually are targeting, multiple countries are targeting now to go ahead with the deployment of the bullet trains, including India. Our networks today are really not ready to support all the real-time communications to be going ahead when you are in a high mobility, for example, 300 kilometers per hour to 500 kilometers per hour. So the new waveforms that we have to go ahead with, OTFS has become a good candidate for this, but that's not the end. We have to integrate maybe the good OTFS or another kind of the waveform designs with a different kind of n-dimensional modulation schemes. We have to go for a sub-terahertz. There is a push for it, which will be enabling you to cover the near field communications or all the near field communications in-house as well as indoor, as well as the outdoor short range communications. We are actually targeting for ISAC that I was saying. But remember, when we will be doing the sensing and communication, the waveform which will be optimal for communication will not be optimal for your sensing. So sometimes the joint waveform design for sensing and communication will be required. Sometimes the different waveforms for sensing as well as communication applications may be required. So we should get ready for it. RIS, when they will be integrated with this ISAC, there also the minute and precise beamforming and your weight designs and your phase designs, control on it, beam space management, all those will be coming into picture. The last but not the least, the security and sustainability. The post-quantum cryptography that we are planning to deploy there, that should be energy efficient fashion from the beginning itself we have to bring into picture. AIML is another key driving feature for us. We are having already the multi-TRP services. We have the enabling intelligent, coherent and non-coherent basis joint transmission schemes coming up. We have to be actually really be thoughtful about that we are going ahead with a massive gigantic MIMO communication structures to enable all this. But what about actually very precise CSI feedback? How will you do it actually real-time basis? How will you do it very precisely? That CSI feedback has to be coming up for the multi-rat communications. We are also should be careful about all the non-linearity that are expected to come on the circuit side for the systems. For example, your all power amplifiers, your phase shifters, your all the driving circuits for the massive antenna structures, that has to be integrated, that has to be thought for. We have to be very sure about the mobility aware seamless handover. For this integrated structure, all the multi-rat, wherever you go, and your very fast mobility included in the structure, that requires this seamless mobility handover. We have to have intelligent CSI feedback, as I have already mentioned. So fundamentally, that was the last slide itself. So fundamentally, actually, it is the 5G core network plus the AI that will be the future for us. So let us join hands together to integrate it seamlessly for our applications for the 6G. Thank you.
Thank you, Professor Devriti. Can I request Professor Eric for his presentation now?
Thank you very much. Before we start, let's freshen up a little bit. Shake your shoulders, stretch your neck. You know, it's been a long day, and there are more talks to come. So then, okay, we're ready. So let's talk machine-type communications. So remember 5G. Okay, so what was new in 5G? Well, to the left, we have the workhorse, mobile broadband, and that was enhanced and was needed to be enhanced. And that continues to be the workhorse also today. But what is the future? What was new in 5G? Well, it was the machine type services, both the massive machine type service and the ultra reliable low latency communications service. Both of these services were new, and I guess somebody said earlier today that the odd generations are introducing stuff which seems interesting but doesn't really work, and then it's the even generations that needs to fix these new innovations. And maybe this is true also in this case, because the pickup of these type of communications has not been exceptional. Okay, and there may be many reasons for that, some technical, some commercial, I don't know, I'm just a professor. All right, but anyways, these needs to be enhanced in 6G. Okay. So one thing that I'm personally is interested in is what's called short packet communications. So it's a little bit of a rabbit hole. So it's dark, it's a little bit moist, it's not so comfortable. But as you see at the light, at the end of the tunnel, there is light. So mobile broadband, you know, this is the workhorse of today's networks. It relies on long packet communications, where packets are thousands of symbols, roughly. Now, control traffic and machine type communication often use short packets, where the entire message is contained in only tens or hundreds of symbols. In that regime, where mobile broadband is not working, is relatively unexplored. There are theoretical tools available, it's been developed in academia for a long time, but they haven't really seen effect in today's systems. So here I think there is a clear potential to do things better. All right, so again, short packets is when we transmit tens or hundreds of symbols, and that contains the entire message. Now, there is room for improvement of this by challenging the way we do things. And the way we do things is to cater for mobile broadband, because that's the workhorse. Okay, so of course the systems have been designed with this that has been driving a lot of the decisions of the design. But we need to do better if we're going to cater for these machine type communication services. All right, so examples include then joint error detection, error control, security, error detection, and error control. And there is something called also unsourced random access that I believe is worthwhile looking into. Now, you can ask me, are these enabling technologies for 6G? Perhaps not 6G, but then I would say evolved 6G could be there. Or why not 7G? All right, that's all I had to say.
Thank you, Eric. Can I request Professor Kawa to make his presentation now?
Hello, everyone. Before I start, I would like to thank the organizer for basically organizing such a fantastic event, and also for the kind invitation. Is it better now? Okay. Thank you. So, our approach towards 6G is basically using terahertz and also quantum. So we know that for 6G is not all about the speed, but also we need intelligence, we need sensing, and also we need trust in the system. So basically, for terahertz, what terahertz brings to us is basically unprecedented data, basically throughput, and also we can go with massive speed and also bandwidths. So mostly when we talk about terahertz, because the definition is normally, we have different definitions for terahertz, but we're talking here about frequency around 100 gigahertz and above. So in that sense, if we go that way, then RF electronics and photonics meet each other. And that brings a lot of advantages for us. So what we can do here, basically building up from devices to circuits to systems, but we need to overcome two challenges. So for example, for terahertz, most of the components are quite bulky, and also they are based on optical excitation. So that brings a lot of challenges when we want to use on-chip integration, when we want to make scalable devices, and when we want to bring integration into the place. So what we are basically, our approach towards these issues are using advanced materials, mostly low-loss materials. So we introducing new materials like superconductors, so they can be operated with very low, basically, power consumptions, with very high efficiency, and with basically photon level control in cheapest scale. So this is one of the main, basically, focus we have at the moment from terahertz side. But for 6G also, we need to have basically native security. We need to have precision timing, both in the level of basically physical layer. So for that, we use the advantages of quantum. So when we use quantum, for quantum communication, we bring quantum communication and sensing together, then we can make ultra secure links like terahertz link with very high speed. We can make scalable distributed quantum computing. And also we can make basically ultra precise localization, all being integrated in the future network platform. So when we bring basically communication, computing, and sensing at terahertz frequencies, then we can bring a lot of advantages in that sense. So terahertz would bring us bandwidths and also speed, as well as sensing, but quantum would allow us to go with security as well as coherence. So these two will make the system quite robust in that sense. which we can make like a quantum Internet of Things operating in very high frequency. So specifically for quantum computing, because our background is mostly from that side, so we have two main challenges. One is scalability, because microwave, most of the basically advanced superconducting and even semiconducting system are operating at microwave. Bringing microwave at very low temperature connected to the conventional optical network is a big challenge. So specifically, for example, the transducers are not very efficient. The bottleneck there is not only that, also we have a lot of wires controlling the qubit in deep cryogenic temperatures. Then the quantum operation, in order to happen, requires at least hundreds or millions of qubits on a chip. So then the number of control and readout lines linearly increases with the number of qubits. So that brings a lot of challenges, specifically for scalability. That's why we are pushing the frequency of the qubit to higher frequency than microwave. So for example, if you operate qubits at terahertz frequency, then we can make the qubit basically chips much smaller. So in the same footprint, we can put much more quantum bits. So that would allow us to make a scalable system. At the same time, we can bring the operation temperature to higher temperature, comparing to millikelvin, which the current technology is operating. So in this case, we can bring basically 16 in that domain, not only for the quantum control and readout, but also for the distributed quantum computing. So microwave in single photon is extremely hard to be transmitted. But when we go to higher frequencies, then, for example, terahertz is much more compatible with optical and conventional, basically, communication system than microwave and at single photon regime. So in order to make this happen, international collaboration is the key, specifically with those countries which can complement the expertise, and we can benefit from each other's basically facility, infrastructure, as well as the basically skills. Thanks so much.
Thank you, Professor Kaba. So I'll summarize, try to summarize what speakers have said in this last half an hour or so. So basically, for 6G, there are these technology goals which can help us in achieving higher speed, lower latency, high security. So what panelists in this panel spoke about, and I think what all of us know, that these are the technologies which will help us in fulfilling these goals, which is ISAC, machine learning, then massive MIMO in 6 to 7 gigahertz spectrum. Then there are these grand goals which 6G should fulfill, and I'll begin with that. So these are basically what we are talking about is the 6G network should be resilient, should be sustainable, should have higher energy efficiency than what 5G could provide. So I'll begin my Q&A with these grand goals, and I think I'll first talk about resilience, and I'll ask this question to Professor Nandana. How can we actually make this 6G network more resilient? You spoke about it. You are doing pioneering work in network resilience. So
yeah, I think this is a question that affects everybody. Different countries. For example, you have, I think recently Spain had a blackout, and so all the mobile systems went out. So you need to power up the system and see how effectively a system can come back from a disruption quickly. So this aspect has to some extent been considered. For example, you can have battery backup and areas like that, but then there are a lot of other things that can go wrong. For example, in a typhoon or flooding situation, and these are still to be taken into account. That's why we are launching this white paper exercise to really gather the feedback from all around the world actually. So yeah, this is a clear challenge at the moment.
So are you, can you characterize this resilience? Is there some metric which you are proposing for resilience?
Yeah, so these are the things to be done in my opinion, like what kind of quality of service or quality of experience, that based on what we define what is a resilient network. I mean, the sustainability, this AI aspects also come into that, I think. Predicting things, whether based on the, training of things. And so these are still to be evolved. I mean, this is not at the moment available in maybe 6G research, but this is to somehow will have to happen.
I'll ask you this provocative question. Can AI ML help in making our 6G network resilient?
I mean, okay, put it this way. Now, whether we like it or not, AI and ML is there. So it's best to take advantage of it in whatever way we can. Of course, somebody in the physical layer may not really believe that there can be, AI ML based channel coding or decoding, because we are already at the channel capacity. But then on the other hand, there are distortions. For example, if you have a power amplifier, there is the non-linearity that needs to be taken into account either at the transmitter side or at the receiver side. So this is also a part of making it resilient, in my opinion. So there are these aspects of machine learning that can be built into from the physical layer and up. So
okay, thank you. So let's talk about sustainability now. So Professor Madini spoke about sustainability. So what needs to be done, Professor, to make the 6G network more sustainable? And how do you, again the same question to you, how do you characterize this sustainability? Is there any metric? Because I keep on hearing that for energy efficiency we have a metric, bits per joule. But for sustainability, we have not, at least I am not aware of any such metric. What is your opinion on that?
Sustainability may be just not the energy part of it. It can include materials, recyclable materials, and so on as well. So there's many factors, like because we are going to next generation, like 6G is the next step. I think we need to take this as a first step to consider for everything sustainable. Like, it's very clear that optical fiber networks, if you're going to increase, the data rates, and if you want to send more and more information, it can't handle the energy levels. So we need, definitely they are after quantum technology now. Like this is like, Nokia has said it, like, they need the quantum technology for the next generation optical networks. So that's kind of the sustainability. We need to think about what foundational technologies that need to maintain the energy level, material. We can't just keep developing without recyclable materials and so on. So everything will come into the sustainability. Okay. Yeah, I don't know any units to say, but it's a general concept.
Fine. And it was incidental that three ladies in the panel actually spoke about QKD, quantum, and security. And this question is posed to all three of you together. That how can quantum help us in making 6G networks secure, and what role do you see quantum playing in that?
Yeah, so basically, especially in the area which I mentioned for example, terahertz, it would be absorbed quite significantly in moisture with air, with basically rain. But what we can bring in with quantum, so we can make quantum sensors, for example, then even if the signal is lost partially, then we would be able to reconstruct it using basically quantum entanglement and the other quantum phenomena which we get. So making, and also quantum would bring a lot of efficiency to the system as well compared to the classical operation. So these would be the advantages which could even revolutionize the field of communication.
Deepa, your take on that?
make it very short. I think it is extremely important to have security, and I think the QKD could get to something that coexists with classical communication. I think it's important to have that.
Okay, so I'm being told that we are running short for time, so I'll keep it short. I'll ask a final one or two questions. Dr. Rao, you spoke about IRS, you spoke about devices, and now when we talk about IRS link, does it really need to be standardized? Another challenge in IRS, which I hear, and as a technologist, which I'm aware of, that like it's not really band specific as of now. Now, if you build an IRS, then it's going to basically amplify other operator signals as well. How do you handle that?
Right. It's a very, very complex scenario. That's what I mentioned there. A true deployment, you expect IRS to be there. You know, only the fixed base station, only that location is known to you. And the user is still moving there, and you expect it to be non-linear communication. We're expecting IRS to be functional and dynamically changing the beam, expecting it to only addressing the user of your choice. It's not going to happen. As you mentioned, it's going to be there. There's always a concern from other users. It's going to saturate probably their devices because of pumping the more energy. But in other way, even today your base station is pumping the energy to every user. So that cannot be the major concern just because IRS is steering the beam. So I don't agree that it's going to trouble the other users, other operators, just because you are using IRS for this. As of now, today deployment, everybody receives everybody's signal. They simultaneously function. Not a problem. The challenge lies more on other side. Is it scalable? Is it scalable? And sensing the user so accurately and who is in motion. Suppose he's going on foot, it's a different scenario. Suppose is traveling there at maybe hundreds of kilometers. Your IRS can sense that fast, identify it, and steer the beam by the time it's already user moved out. How fast you can steer the beam, because you are pointed beams now. As per the base station, currently you have larger beam widths, it can cover the larger area. And with IRS, thinking about the large amount of the maybe thousands of elements on the panel and get a very highly directed beam, probably still you miss the link. So these are the places where the algorithms, what has been considered without considering the physical aspects of it, is probably that need to be fine-tuned to say that IRS is a reality. Otherwise, technology-wise, it does the job what's supposed to do. But still long way for thinking that it's going to be a deployable solution.
Thank you. Eric, one last question to you. What's wrong with today's machine type communication?
Well, I think the main problem is that it's too expensive. And why is it too expensive? I think it's because the requirements put on these services has been ridiculously hard to follow. And why are they that? And I think it's because the verticals are asked for too much. Instead of thinking about what can we do if we co-design the vertical application with the communication system, we can get something which is viable. So that, I think, is my analysis. It's simply a mismatch of expectations from the verticals that has not been challenged enough. We should have said, we can do this for you. You can get this performance, but you won't like the price. And then we could have had another discussion. That's my point.
Thank you. So we have very little time for questions from our audience. So if there are one or two questions, we can take them. Otherwise, we'll have to wrap it up.
Yep. Hello, I want to ask two fast questions. One is that you are talking about, Madam Sen, you are talking about the CSI feedback. Normally, we are taking the channel quality index, rank indicator, and pre-coded matrix indicator. Are you considering any fourth or fifth indicators to be part of this CSI feedback? That is number one. And number two is that you are talking about the non-terrestrial communication over here. how do you think the interoperability issues with the existing terrestrial communications, because there will be a lot of latency issues over the satellite? So these two questions.
Okay. As a first question to answer, the CSI for the future generation network not only will be what the way we are doing today. For example, we will be doing the massive beamforming, right? With the mobility, if we consider, then the range estimation as well as the angle estimation, the joint range and angle also should be coming as a feedback. If I talk about the very high speed communication, so V2V communication suppose is going on, or satellite to satellite communication is going on. In that case, the speed with which the CSI should come back, it should be almost real time. Otherwise, you won't be able to quickly change the beam directions from the transmit side. So whatever today we are doing, with that, the range estimation, the phase estimation, joint range and phase estimation, minimum this three has to come back. And the second thing to go ahead with, yes, for the non-terrestrial networks, especially for satellite communication, we understand that there is a big latency involved in it. So that latency part has, if we wish to integrate the joint space, air and ground communication, this latency part has to be within the design of the waveform itself as well as the communication protocol itself, we need to think of to address it.
Hello, sir. Everyone is saying that 6G technology would give a new devices. The existing devices would be obsolete, and we would get a paradigm shift of getting a new devices. Is it true, or with the devices which is being used now would be used, or we should be inventing or moving forward on new devices? I don't.
See, devices, it's always function of the frequencies what we use. As the technology changing, so what are you using for the 4G is not used for 5G, we moved to 3.5 gigahertz. Now we expect it to go to 7 gigahertz. None of the device is going to be useful. But doesn't mean that the entire, not that you use the same phone for 4G to 5G to 6G, but as per the technology, we are building the solution, leaving the front end radio, remaining things still is doable. What is happening in the processing and the, as I said, waveforms, all those things still works on the digital domain. Only what's going to change predominantly as per the way the cost involved, the change is going to come there in the radio front end. So that's moving from 3.5 gigahertz to 7 gigahertz. That's the way the challenge is going to come there.
We are running out of time now, so let's thank the panelists for their informative talks and for coming all the way here and participating in this panel discussion. Thank you.
So I thank the moderator and the session speakers. I request our moderator to please present token of appreciation to each of our panelists, starting with Professor Matheny. Please have a round of applause. Dr. Rao from Samir. Professor Nandana. Professor Eric. Professor Debrati. Thank you. Professor Deepa. Professor Kave.
I request Professor David or the Patrick sir, please give token of appreciation to our chair, Professor Rohit. Please have a big round of applause. So now we have a short tea break. After that, we will conclude. We will start with a keynote address.